Welcome to Root Research, where we decode science in plain language. Today we want to tell you about how astronomers are using millions of distant cosmic lighthouses, quasars, to set new limits on the faint hum of gravitational waves vibrating through the universe, discovered and explained by Jeremy Darling and collaborators. Let's start. Imagine the universe as a giant ocean. Gravitational waves are like ripples on its surface. You feel water move when a wave hits the shore. But what if the waves are so gentle they take years or decades to pass? That's what scientists are trying to detect, the most subtle ripples in space-time that fill the cosmos. These ripples are called the stochastic gravitational wave background, a constant faint hum created by countless sources like massive black hole pairs merging over cosmic time. Some of these waves were recently seen using pulsars, nature's precise cosmic clocks. But that only showed part of the picture. So what did Darling and his team notice that's different? Instead of using pulsars, they looked at the detailed sky positions and motions of over 1 million quasars, super bright cores of distant galaxies shining across the universe. These quasars are so far away that, in normal conditions, they shouldn't appear to move relative to each other. But if gravitational waves rip through space, they can make the apparent positions of quasars jiggle just a tiny bit. Like watching distant objects drift ever so slightly on the horizon. To do this, Darling used data from the Gaia mission, a space telescope that measures positions of stars and quasars with extraordinary precision. Instead of looking at each quasar alone, he looked at pairs, over 2 billion pairs, and checked whether there's any correlation in the way their positions change depending on how far apart they are on the sky. This kind of curve describing how the motion of one quasar relates to another is called the Astrometric Helling-Downs curve. The first time it's been built using positional, not timing, data. Why does this idea matter? In everyday life, we understand that if you stand on a trampoline with someone else and someone jumps in the middle, you both move. And the way you move depends on where you are. Gravitational waves are like that jump. They stretch and squeeze space in all directions. But you need a reference frame. Many different points you can compare to see the effect. For the universe, quasars are our trampoline points scattered across the sky. And here's the key. Darling didn't find a definitive detection of the gravitational wave hum yet, but he did set the tightest limit so far on how strong that hum can be using this method. Tighter than previous optical methods and even better than some radio techniques. Let's take a real-world example to bring this home. Imagine you're at a huge outdoor concert with tens of thousands of people holding LED wristbands. If someone waves a laser pointer in a pattern, the bands light up in sync and you can see a pattern. That's like pulsar timing. Precise, but along one line of detection. Now imagine that tiny breeze blows through the crowd. You can't see the breeze, but the direction and timing of the wristband shifting can tell you something is happening all around. But you need to look at patterns between multiple wristbands to understand it. That's what Darling's work is, looking at correlations across the whole crowd, not just individual changes. What does this tell us about gravitational waves? Darling's team calculated that if gravitational waves at very low frequencies, waves that take years to cycle, were stronger than a certain amount, we would see them in the quasar motions. But we don't. That means the universe's gravitational wave background must be even fainter than some theories predicted. Specifically, they found the gravitational wave energy must be below a very small threshold. Think microscopic wiggles in space-time, in the frequency range they're sensitive to. In other words, the universe is quieter at these long wavelengths than we might have expected. That's huge because this helps scientists rule out some exotic theories about what the universe might be doing. And it tells theorists they need to refine their ideas about how common or loud these cosmic ripples really are. What's the broader significance? Darling's method is pioneering. It's the first time optical astrometry, precise position measurements, surpassed older radio methods in setting limits on gravitational waves at these enormous timescales. And as telescopes get better and we collect more years of quasar data, this approach could eventually detect the gravitational wave background directly, not just constrain it. It's like listening for the hum of the universe with ever more sensitive ears. This helps answer some deep questions. What produces most of the gravitational wave background? Are there unknown massive black hole mergers hiding out there? Or even stranger physics? Darling's constraints help shrink the set of possibilities and guide future research. The main takeaway? Quasars across the sky are being used as cosmic motion detectors. Darling and his collaborators created the first astrometric Hellingsdowns curve from quasar pairs. They set the strictest limits yet on how loud the low-frequency gravitational wave background can be. This helps narrow down what the universe's gravitational hum might or might not be made of. Thank you to the scientists pushing the boundaries of cosmic exploration. If you like what we do, subscribe and write a comment.